Hey, I'm Joe Schmidt, and this is The Majesty of Reason. Today we're going to be looking at paradoxes of infinity, and boy, I am infinitely excited for this. So I should probably start with what a paradox is. A paradox is some sort of situation or hypothetical scenario or even argument that leads to either an incredibly strange conclusion or a contradictory conclusion, but whose premises all look, pretty plausible, at least on first glance. You have the liar's paradox, for instance, like this sentence is false or I am lying. Well, if that's true, well, then it's false, right? But if it's false, well then it's true, right? So it's like it's true if and only if it's false. So it's like completely paradoxical. It's like what the heck? Like where do we go wrong? And so that's a general account of what paradoxes are. And infinity is that is the cardinality or the number of the natural numbers from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all and so on, or the cardinality of the positive integers or the cardinality of all integers or what have you. There are a lot of ways of putting it. It also is characterized by Cantor's property, which is basically that a set has members whose cardinality is a left null or infinity as we're understanding it here, um, provided that a proper subset can be lined up with the subset as a whole in a one-to-one correspondence. So, for instance, the natural numbers can be aligned with the positive even numbers such that there's a one-to-one correspondence between the two sets. Like you can just pair 1 with 2, and then 2 with 4, and then 3 with 6. And so for any number n, you pair it with 2n. And so by that we get a sort of, we can see visually Cantor's property as applied to the natural numbers and a proper subset of them. So with enough preliminaries out of the way, we can get into the paradoxes, so the fun stuff. So some paradoxes of the infinite make use of what's called supertasks. And supertasks, that's just basically performing infinitely many tasks or operations or processes or actions within a finite interval of time. So for instance, you would do something at 1 minute until 12, and then you do another thing 30 seconds till 12, and then 15 seconds till 12, and then 7.5 seconds, and then 3.75 seconds, and so on and so forth ad infinitum. And so you'd actually perform infinitely many tasks before 12 in this case. That would be a super task. By contrast, other paradoxes of the infinite employ an infinite past. That is to say, a beginningless past where we don't have to have the sort of intervals of time getting smaller and smaller and smaller. We can actually just have constant intervals of time, like a year, for instance, because if the past is beginningless, well, then there are obviously infinitely many years, as it were. We could use seconds or whatever metric of time that we wish. So one such paradox derives from Jose Bernadetti. I think I pronounced that right. Some people will say Bernadetti, other people say Bernadette or Bernadette. I don't know who's right, so but it comes from his Infinity, an essay in metaphysics, his 1964 book. And what he does is he asks us to imagine a victim. Let's just call this victim Fred, who is assailed by an infinite number of executioners, or at least would-be executioners. We can call them Grim Reapers. Now, each Grim Reaper is assigned a deadline between, let's say, midnight and 12:01 a.m. If a Reaper finds Fred alive at its assigned moment, say because no earlier Reaper killed him, well, then that Reaper kills Fred. If an earlier Reaper has already killed Fred, well, then it just does nothing. Okay? Now, the Reaper's assigned deadlines are arranged like so. Okay? Reaper number one's deadline is 12:01. Reaper number two's deadline is 30 seconds after midnight. Reaper number three, it's 15 seconds after midnight, and so on ad infinitum. In this case, there's no first Grim Reaper, at least in the order of time, right? In order to survive any finite period after midnight, Fred must escape an infinite number of earlier deadlines, which is, per hypothesis of what the Grim Reapers do and are, that's not possible. But okay, so with the setup, laid bare, we can now get into why this story leads quite quickly to a contradiction. or at least it leads to a contradiction on the assumption that Fred does not die unless one of the Reapers kills him. We actually don't quite need this assumption for this kind of supertask Grim Reaper scenario. We can cash it out in terms of placing a particle in a finite distance from a plane. Rob Koons develops this in some of his papers and some of his works, but let's just go with this rather innocuous assumption that Fred doesn't die unless one of the Reapers kills him. We can just assume that, he and his immediate environment, as well as the Reapers, that's all that there is in this world that we're considering. So it's an innocuous assumption. But we do get a contradiction here. So why is that? Well, let me explain. So we know that at least one Grim Reaper must act, right? So because if all the Grim Reapers whose numbers are greater than 1 do nothing, well then Reaper number 1 will act. Yet we can actually show deductively that it's impossible for any Grim Reaper to act, since for any number n, Grim Reaper number n cannot do so unless Fred survives until its assigned deadline at whatever seconds, it's actually 1/2 to the power of n seconds after midnight. But it's simply impossible for Fred to survive that long, since Fred's surviving until Reaper number n's deadline entails that no Grim Reaper with a number larger than, for instance, n plus 2 has acted, but in that case, Reaper number n plus 1 must have acted, right? If all the Grim Reapers larger than n plus 2 acted, well then, per our definition of the Reaper, of the Grim Reapers in our scenario, Reaper number n plus 1 would have killed him, because he looked, he saw that Fred was still alive, and it would have killed him. But what this shows is that for any number n, Grim Reaper number n cannot kill Fred. But yet, we already know that at least one of them killed him, right? But yet, none of them killed him, right? So we actually do get a contradiction in this scenario. And of course, we can modify and eliminate certain aspects of the Grim Reaper scenario in order to eliminate like extraneous elements, like assuming that Fred does not die unless one of the Reapers kills him, because we can cache it in terms of particles or what have you, and so on and so forth. So that's at least the supertask version of the Grim Reapers. And so next we're going to turn to paper passers, and we're going to look at an infinite past version of that. So suppose we have an infinite series of paper passers labeled with all the natural numbers, so number 1, 2, 3, 4, 5, and so on. And these can either be, well, they can either be persons or machines or angels or what have you. It doesn't really matter. Let's just call them a paper passer. They perform some sort of action, and an action that I will specify in a moment. Okay, and so these paper passers, they each, similarly to the Grim Reaper scenario, each of the paper passers has a deadline, but in this case it extends infinitely far into the past. Okay, so paper passer number 1 does its job, and I'm going to specify the job soon, does its job at, let's say, January 1st, 1 BC, or BCE if you prefer. Paper passer number 2 does its job on the same day, 2 BC. And then paper passer number 3 does its job on the same day, 3 BC, and so on ad infinitum into the beginningless past. Now, what action are these guys performing? Okay, so the action is that they are going to be receiving a paper from the previous paper passer, okay? And what they do is they check to see if there's a number written on that paper. If there is a number written on that paper, then they do nothing, and they simply pass it to the next Grim Reaper who does his action a year later, okay? And so he passes it to the Grim Reaper with a number that is 1 less than his, and that Grim Reaper is going to do his job 1 year later. By contrast, if there is no number when the paper passer receives it on his on the date of his deadline, right? Let's say 4 BC or whatever, January 1st, 4 BC. Well, then this paper passer is going to write his assigned number on the paper and then pass it to the next paper passer, who in turn is going to perform the same sort of procedure that we've been doing. That next paper passer will look at the paper, see if there's a number. In this case, there will be a number because we're supposing that number 4 wrote it, and he won't do anything, and he'll just pass it to the next paper passer. So that's the setup. Once again, however, we're going to be getting a contradiction here. And why is that? There has to be some number on the paper by 1 BC, right? Because if there's no number on the paper by 1 BC, well then the paper passer that is assigned the number 1 will write its number, okay? So there has to be some number on the paper by 1 BC, okay? So let's just call that number n, okay? We're going to call that number n. There has to be some number on the paper by the end of this process. But what number is it? That's the question. In fact, it can't be any number. It cannot be any number because in order for number n to be written on it, n would have had to received the paper from the earlier paper passer with no number written on it. But if n received the paper from an earlier paper passer with no number written on it, well then that means that the earlier paper passer from whom the number n received the paper, that means that that paper passer failed to write his number, right? But we suppose that each paper passer is performing this procedure, right? And so it's not possible for that paper passer to fail in this case because we've already built that into our scenario that that paper passer is such that if there's no number on it, then it would write it. So in that case, paper passer n plus 1 would have already written his number on the paper, in which case paper passer number n did not. But we literally just assumed for reductio that paper passer number n did. So completing our reductio, we get that there both is and is not number n written on the paper. And that's a contradiction. Don't worry too much about solutions right now. We'll be talking about some of those near the end of the video. So you'll just have to be, on the edge of your seats until then. So the next one is, the next paradox that I want to consider is Thomson's lamp. Okay, so imagine we have a lamp and it's got a little switch toggle that we can switch it on or off. In fact, I can probably simulate the noise right now. You like that? Yeah, you like that. Anyway, Thomson's lamp has a little switch toggle and you can toggle it on or off, right? On or off, on or off, okay? And so let's get a supertask going. So let's talk about midnight, okay? We have midnight, and that is going to be the end state of our process, and we're going to start 1 minute until midnight. Okay, and so we're going to toggle the switch at 11:59. Okay, let's say we turn it on or off. It doesn't really matter. Okay, fine. Let's say we turn it on. It was initially off, so we turn it on at 11:59, and then half the distance until midnight from whatever we just did. We wait until half that distance, and then we toggle the switch again. Okay, so then at 11:59 plus 30 seconds, we toggle the switch and we turn the lamp off, okay? And then we wait another 15 seconds because now that's half of the 30. And then we toggle the switch again. So we just turned it on, okay? And then we wait another 7.5 seconds and we toggle the switch again, okay? And we don't have to be the ones that toggle the switch. We could do some sort of angel that causes it to happen or whatever, that maybe there's some machine that causes it or whatever. But what's going to happen is that we're going to toggle the switch infinitely many times before the deadline of 12 o'clock arrives. But then the question is the lamp on or off at 12 o'clock? Just think about it. I mean, this is really puzzling. On each occasion that we turned the lamp on, there was a subsequent occasion right after it that we turned it off, right? So literally every time we turn that lamp on, we almost immediately switched it off, right? So it seems incredibly odd to say that it's on at the end of the procedure, right? Because literally every time we turn it on, we followed that almost immediately by turning it off. But on the flip side of things, get it? On the flip side, we're like flipping a toggle switch, huh? But on the flip side of things, how on earth could the lamp be off? I mean, every time we toggled and we flipped the switch off, almost immediately after that, we turned the lamp back on. So, I mean, how could it be off? I mean, this is deeply puzzling. So we don't quite have a contradiction yet, but it seems as though we do get a contradiction when we add into the mix the PSR, or at least maybe even a very modest PSR that's a sort of a mundane PSR. That is, a PSR that applies to, objects and events and occasions and states in ordinary experience, namely things like, the states of lamps and their toggles. These things have explanations. That seems to be a relatively modest and mild PSR. But when you add that in, we actually get a contradiction. Why is that? Well, there is simply no explanation for why the lamp is on or off, whichever one it is, at 12 o'clock. And we can simply see that by, contemplating the scenario that led up to the state of the lamp. And we can suppose that the lamp's state was only affected by the toggle switchings. Because if it's on, there's simply no explanation for why it's on. Literally, every time we turn it on, we immediately turn it off. So there's no reason as to why it should be on after the process is over, at 12 o'clock. But by parity of reasoning, we're going to get the same conclusion as to why the lamp is off. And so it seems as though we have a violation of the PSR, or at least a violation of the mundane PSR. And so the PSR is both true and false, or the mundane PSR is both true and false, and that's contradictory. And again, we'll be able to visit some potential solutions near the end. Okay, so let's turn to another sort of paradox of the infinite. So suppose we have an infinitely large, and this one's called Ross's urn. Suppose we have an infinitely large urn and infinitely many, say, ping pong balls, okay? Each of which has a unique natural number on it. So like 1, then 2, then 3, then 4, and so on. Suppose further that the urn is originally empty. So, well, I mean, apart from like the air and stuff, but there aren't any balls in there. So we're going to perform a process here. And it could be us performing it, it could be an angel performing it, again, it could be like a machine performing it, who knows. But we're going to perform a process, let's call it process 1, okay? And this is going to proceed like so. So first, we're going to add 10 balls to the urn. And these are going to be the 10 balls that have natural numbers of lowest cardinality, that is just to say the smallest numbers, the 10 natural numbers of lowest cardinality from the natural numbers that haven't yet been in the urn. We're going to add those 10 balls to the urn, but then we're going to remove the ball inside the urn from from all the ones that are so far in the urn with the natural number of lowest cardinality, okay? And then we're just going to repeat this procedure for each step and perform infinitely many such steps. Don't replace the balls, okay? And so what is this going to look like? I mean, I guess I should be a little bit more concrete. So in step 1, we're adding in balls 1 through 10, and then we're going to take out ball 1. In step 2, we're adding in balls 11 through 20, and then we're taking out ball 2. In step 3, we're adding balls 21 through 30, and we're taking out ball 3, and so on ad infinitum. But now consider a different process, process 2, okay? Each step of process 2 proceeds like so. First, add 9 balls, okay? These 9 balls are going to be the 9 natural numbers of lowest cardinality that haven't yet at least been in the urn, okay? So we're adding 9 balls to the urn. But then what we're going to do is we're going to take the ball in the urn with the number of lowest cardinality, and we're going to draw a 0. We're going to upend a 0 on the end of it, okay? And we thereby multiply it by 10. So what we're doing is we're adding 9 balls, and then we're taking the ball of lowest cardinality, and we're multiplying it by 10, basically, by drawing a 0, or printing a 0, or what have you, okay? And so in the first step, we would turn 1 into 10 by writing a 0 on it. And then in step 2, we would turn ball number 2 into 20, ball number 20. And then in step 3, we turn ball number 3 into ball number 30, and so on. And then we're going to repeat this procedure for each step, perform infinitely many such steps. Okay, so we therefore have 2 processes, and the cardinalities of their steps are identical, namely aleph null, infinity. And moreover, the end state of the system, namely the urn, after each step of each process is completely identical, right? Balls numbered 2 through 10 are present in the urn after both process 1 and process 2, and then balls numbered 3 through 20 after step 2 for both urns, and then, balls numbered 4 through 30 after step 3, and so on. And more generally, for each step n, the end states of the respective systems, namely the urns, are completely identical. Well, at least qualitatively identical. You get it. But now a strange question arises. What are the respective end states of the urns as a whole and their contents upon completion of these 2 processes? Well, let's begin with the end state of the system after performing process 1. Importantly, there cannot be any balls left in the urn. This is because at each step, the ball that step's number on it is removed. For any ball number, there is a step number at which it is removed. And indeed, if there's a ball left in the urn at the end of the process, well, then it will have some natural number n on it. But if n's written on it, well, then that ball was removed at step n. That's precisely how we specified process 1. But if that ball was removed, since it wasn't replaced, it's not in the urn. And so what we get is that there's no ball left in the urn at the end of process 1. But now consider the end state of the system after performing process 2. Interestingly, there are infinitely many balls in the urn. After all, we never removed a single ball. All we did was add balls. In fact, the contents of the urn at the end of process 2 are infinitely many balls on which are written all the natural numbers, each followed by an infinite string of zeros, what mathematicians call an omega series of zeros. Okay, I think it's an omega sequence of zeros. Maybe. But now, just think about how crazy this is, right? The end states of the 2 urns are exactly identical for literally every process, for every step within these 2 processes. Every single step is such that the end state of that step, of the urn, is literally identical in both cases, process 1 and process 2. It's literally the same. And yet somehow, at the end of these processes, one of them has no balls in it, and the other one has infinitely many balls. That is insane. Like, just think about that. That's insane. So I think that goes, sufficiently far into the paradox that we need for present purposes. So let's turn next to an infinite fair lottery. Okay, so suppose we can construct, or not can, let's suppose we do construct an infinite fair lottery, okay? A lottery in which an infinite number of outcomes are possible with exactly the same probability. For instance, let's suppose that it were possible to flip a coin an infinite number of times, with each flip assigned its own unique natural number, and to assemble all the results into a single lottery winning announcement. Now, if this is the case, it would be possible for all but one of the flips to come out heads. That's metaphysically possible, in which case the sole result that came up tails would pick out the corresponding natural number, its own unique natural number that we assign to it, as the winner, okay? This would be an infinite fair lottery, since each number would have, by, considerations of symmetry, an equal chance of being the quote-unquote winner. Now, it's a little subtle, but we've already reached an impossibility, since if this occasion were to occur, it would force us to violate principles, necessarily true principles of rationality that are fundamental and essential. I'll just illustrate one piece of this, and this is deriving from Alexander Pruss's work, specifically in his book Infinity, Causation, and Paradox. He goes into a lot more detail about why these principles of rationality are fundamental and essential, and so on and so forth. So while I won't be able to give a sort of, sufficiently exhaustive characterization, it'll be good enough for present purposes. So let me describe how we can violate certain principles next, but just know that it won't be a completely exhaustive accounting. For an exhaustive accounting, definitely check out Pruss's wonderful book. Okay, so what are we violating? What principles of rationality that are fundamental and essential are we violating? Well, suppose that you and I both ran such lotteries, and in both cases there was a winner. Now, no matter how large my number is, I should assign a probability of 1, or some number infinitely close to 1, that any other natural number selected in another infinite fair lottery is larger than mine, right? I mean, this simply falls out of the fact that there will be only finitely many numbers smaller than my number, and infinitely many greater, right? Pick any number n, there are infinitely many numbers greater than that, but only finitely many numbers smaller than that. And when you do the probability calculation of what you should assign probabilities to someone else's number being higher compared to its being lower, well, you're basically going to get a probability of 1, or at least a number infinitely close to 1, that any other natural number selected in another infinite fair lottery is larger than your own number. Now, again, we're supposing that both you and I, we each have a number for our respective lotteries. And we each want to, whichever one of us has a larger number, right? We want to own that larger number, because we just deduced, right, that we should assign a probability of 1, or at least a number infinitely close to 1, that any other natural number selected in another infinite fair lottery as a winner is larger than mine. So we want to own the larger number of at least our two numbers, right? And so we each prefer to, quote unquote, own the larger number as our own. And in that case, we have an overwhelmingly strong reason to prefer the other person's unknown number to your own, okay? Because, it's almost certain that their number is larger, and the larger ones give you a greater chance of winning the lottery. But here's the kick. You would have an equally strong reason to prefer my own number to yours for the same reasoning that we've been going through, right? Like, we've been going through this reasoning for me. I've been reasoning, okay, well, it's almost certain that the winning number in the lottery is a number larger than mine. And so I really, it's almost certain that your number is larger than mine. So what I should be doing is I need to get a hold of your number, dear listener. But you go through the same reasoning process, and you are saying, oh man, it's almost certain that I need to get Joe's number. And so what we get in such a situation is that we could both be exploited by a third party in what's called a Dutch book problem. These are paradoxes of rationality. Whenever something entails a Dutch book, you went wrong somewhere. in such a situation where we're both like, man, I really need to own that other person's number. In such a situation, we could both be exploited by a third party Dutch booker who is completely ignorant of both of our numbers and who can induce each of us to bet against our own number as the greater. That is to say, we're going to bet against our number as the greater. That is to say, we're betting for that the other person's number is greater than ours. And so we'd be utterly powerless. We'd be completely exploited by this third party Dutch book. And this is a paradox of rationality. You always want to avoid a Dutch book scenario. That means that you are guaranteed to lose money. And it's impossible for you to be a rational agent and yet be guaranteed to lose money. That means you went wrong somewhere. Because rational agents should be able to assign their credences in such a way that they avoid inconsistent credences, because inconsistent credences lead to Dutch books. But in this infinite fair lottery, right, there's no way to rule out our being exploited, unless, of course, we adopt causal finitism or finitism simpliciter. And so this is what's called a paradox of rationality. And if you want to learn more about this, again, I said I can't be exhaustive. You're gonna have to check out Alex Proust's book and the wonderful stuff that he has in there on infinite fair lotteries. But what I characterized is sufficient for present purposes. Okay, Hilbert's Hotel. I'm not going to spend too much time on this one because I'm sure the listeners are acquainted with William Lane Craig and his work. But Hilbert's Hotel is basically a hotel that is infinitely accommodating. That is to say, it has an infinite number of rooms, and we can suppose that all the rooms are filled, and then we can suppose that someone comes in to the clerk at the check-in desk, and the person's like, "Hey, I need a room," and then the person's like, "Well, we're all full, but I can accommodate you," and so the clerk takes the person in room 1, forces them to shift to room 2, the person in room 2 shifts to room 3, and so on and so forth. And so we went from an initially full hotel to having one vacancy where we can accommodate this one person. And we can do a similar thing if literally infinitely many guests arrived, because we can take each person in room number n and shift them to room number 2n, in which case all the even numbered rooms are occupied, but now all the odd numbered rooms are vacant. And so we can actually fit in an infinite number of guests into a hotel that was originally full. We can also, of course, do subtraction. So if 3 guests left the hotel when it's infinitely full, subtracting 3 guests, I mean, that's not going to make a difference to the cardinality of the guests in the hotel because it's still infinitely many. But if guests if all the even numbered guests left, well, then we just subtracted an infinite number of guests, but we still have an infinite number of guests in the hotel, and they could just shift around to refill the hotel, and that's despite the fact that infinitely many just left. And moreover, we can also have infinitely many guests leave who are in rooms numbered, let's say, 3 and above. But in that case, we would literally have a hotel that's completely vacant except for guests in rooms 1 and 2. And so it's kind of weird that you can subtract the same number of guests in this case, but yet result in different configurations or different numbers of people in the guests in the hotel after such arithmetical operations. I'm going to be honest, I don't really see much wrong with this. In a lot of our other situations, we've been actually able to derive a contradiction. We've been able to show some sort of like extreme bizarre situation or so on and so forth. But in Hilbert's Hotel, I mean, to me, it seems like, yeah, I mean, that's precisely what you should expect. Where's the contradiction here? Can you tell me where we went wrong? It's just I mean, I don't even see what's wrong with, subtracting. I mean, what matters is what this shows us is that the way that we subtract guests matters. I mean, obviously, we couldn't go in 2 scenarios and subtract guests 3 through infinity in both scenarios, and yet somehow in one case, have infinitely many guests in the hotel, and in the other case have finitely many. But I mean, what matters is the way or the manner in which we take out guests. And I mean, this is precisely what we should expect if it's an infinite hotel. And I mean, we haven't derived a contradiction anywhere. I mean, at best, we've just said oh well, it was originally full, and then we moved some people around, and then we accommodated more. But where's the contradiction in that? There seems to be nothing incoherent here. Yeah, I mean, this is precisely what we should expect if the actual infinite could be the case. Whereas in a lot of our other cases, we've literally been able to derive a contradiction, like Fred is both alive and dead at, let's see, what was it, 12 a.m.? I think I used 12 a.m. at that one. Or a violation of the PSR, for instance, or what have you, or a paradox of rationality, or that there both is and is not a number on the paper. Whereas in Hilbert's Hotel, it's just where's the contradiction? I mean, what's absurd about this? At least that's speaking from my own, at least my own epistemic stance. And so also, what we get a paradox of allowing infinite causal chains in terms of vicious circularity. Now you'll be able to see. I think that's a chicken. I searched up chicken and that came up. I hope it's not like a rooster. Is a rooster like a female? Is that a hen? I don't know all the distinctions. Maybe you can illumine me in the comments of this video. But I'm just going to call this thing a chicken. I don't know why I'm going on about chickens, but okay, vicious circularity and infinite causal chains. I'm going to do a sort of abstract version of this paradoxical situation, and then I'm going to bring it back to chickens, and it'll be more concrete, because, I mean, who doesn't love chickens? What we get is that causation, or at least explanation, cannot be circular, and so, or at least viciously circular. So, for instance, if we're trying to explain why the sky is blue, well, then we can't explain why the sky is blue in terms of the skies being blue. Similarly, we can't explain why 3 Eskimos are on a corner simply by saying Eskimo 1 is there because Eskimo 2 is there, and Eskimo 2 is there because Eskimo 3 is there, and Eskimo 3 is there because Eskimo 1 is there. Like, that explains nothing. We've literally just gone in a vicious circle. And so it stems from the idea that explanations or causations or causes are supposed to be prior to their effects, and hence, if something were to cause or explain itself, well, then it would be both prior to itself and not prior to itself, which is, obviously absurd. So what we get is that we can't have circularity with respect to causation or explanation. But as Alexander Proust, again, in this book, has pointed out, there is a connection between the prohibition of circular explanations and the prohibition of causal regresses. So suppose that there is an infinite causal regress, and we could say that it has the form of number 1, number 2, number 3, number 4, and so on, these different substances or causal entities. Going at an it could be a simultaneous series of causes, or it could be infinitely far into the past, but what matters is that we have an infinite series of causes, a causal regress, such that each number is caused by that number plus 1. So number 1 is caused by number 2 is caused by number 3 is caused by number 4, and so on ad infinitum. But consider now the existence of the even-numbered entities, right? We can call the plurality of the even-numbered entities E, and the existence of the plurality of the odd-numbered entities. We can call that plurality O. Now, E, crucially, is causally explained by O, right? Because every member of E is immediately caused by a member of O. But for exactly similar reasons, the plurality O is causally explained by E. And since such circular explanation or causation is impossible, an infinite causal regress must ipso facto be impossible as well. Proust gives a really nice discussion of this in his book. He talks about certain strengths and weaknesses of the argument, so you could check that out for further information. And I did talk about how I was going to concretize this with respect to chickens. So let's imagine that we have blue chickens and red chickens, such that a blue chicken is caused to exist by a red chicken, and this red chicken is then caused to exist by a blue chicken that was earlier than it, and then the blue chicken is caused by a red chicken, and so on ad infinitum. So we've got infinitely many chickens, plenty to fill your tummy with chicken tenders, but we're not going to kill them yet. And maybe it's not ethical to kill them. Who knows? You could talk to Mike Humer or some other people on that. I'm getting ahead of myself. Okay, so we've got the infinitely far back in the past. We've got one red chicken caused by a blue chicken caused by a red chicken caused by a blue chicken caused by a red chicken. Well, we can ask, okay, what explains why red chickens are in reality? Well, obviously the blue chickens. I mean, the blue chickens explain it because literally every single red chicken is such that it's caused to exist by a blue chicken. But what explains why blue chickens are in reality? Well, because the red chickens are in reality. The blue chickens are explained by the red chickens because each blue chicken is such that it's caused by a red chicken. But in that case, we have a sort of vicious circularity. The plurality of blue chickens is explained by the plurality of red chickens, but the plurality of red chickens is explained by the plurality of blue chickens. And so we get a vicious circularity. And so this is supposed to be a paradox, yet another paradox of the infinite. Okay, so I'm not going to talk too much about the solutions and implications. You can check out Alexander Proust's work more on this. You can check out Rob Koons's work on this, and so on and so forth. But there are lots of different assumptions that we made throughout each procedure that could be challenged. You could challenge the assumption that time is or can be continuous. That is to say, if time is continuous, that means that for any two times t and t prime, there is a distinct time in between those times. Or you could challenge the idea of an infinite past, or you could challenge the idea of traversing an actual infinite, or you could say that the culprit here is the assumption that causal chains can be infinitely long. So what you would do is you'd kill all the paradoxes by adopting causal finitism, or you could adopt finitism simpliciter that just says like the infinites just aren't in reality, not at all. They're only sort of in our concepts and we can play with them, but they don't make their appearances in abstract or concrete reality at all. You could challenge various patchwork principles. These patchwork principles are principles of modal epistemology, and they basically say that if you have an isolated scenario that is possible, and you have a different possible world such that it has enough room, as it were, to accommodate this isolated scenario repeated or duplicated multiple times, well, then there's a third possible world in which you have that backdrop with those intrinsically duplicated scenarios. So if there's a chicken is possible, or like an isolated, let's just say a particle is possible, and you have a different possible world in which you have enough room to accommodate infinitely many such particles, well then this patchwork principle says that you can sort of patch these particles together within that framework, and you'll get a resulting possible world in which there are these infinitely many particles. And so we could challenge patchwork principles. We could also challenge the idea of like instantaneous action, because a lot of these paradoxes required that either a Grim Reaper or some sort of mechanism was able to like instantaneously cause something. We could challenge the idea of infinite intensive magnitudes, so things like infinite speed, because when we were doing those lamp togglings, for instance, the distance that the toggle traverses in the whole process, well, it's an infinite distance. It gets flipped up and down and up and down, but it's only in a finite amount of time. So infinite distance divided by finite amount of time equals infinite speed, and so we could try to rule out infinite intensive magnitudes. Proust goes through a lot of these, and he brings out some really interesting implications from some of them. And what's interesting also is that some of these only target like one paradox, and there are a whole host of paradoxes that it doesn't even target, like that instantaneous action one. It's like we can formulate a lot of these paradoxes that don't even require instantaneous action, and we can also formulate the exact same paradox that it was trying to target. We could formulate that in an alternative way and still derive a contradiction without instantaneous action. Similar to things like continuous time. For a lot of these that use continuous time in supertasks, we could actually just run the process as an infinite past. If someone's trying to talk about infinite intensive magnitudes, well, we don't have to talk about physical quantities. We can talk about like angels, for instance. And we have an angel that thinks about 1 and then thinks about 0, and then thinks about 1 and then thinks about 0 in its mind, and then we can perform an infinite process, like a super task, and then we can ask at the end what number is on its mind. We can suppose that it doesn't like change or alter its mind from either 0 or 1. But which number is it? Like for all the same reasons on the on and off lamp switch, we're going to be able to leverage those reasons in the case of the angel, right? And so talking about infinite intensive magnitudes with respect to physical quantities and so on, we're just not going to get that in the case of an angel, because there are no physical quantities. There is no like speed or distance or so on. So a lot of these are such that you can try to employ a killer for one of them, but it's going to be able to be reworked in such a way that it avoids whatever you tried to avoid it with. And so what Proust tries to do in his book is he says, look, we have a solution to all of these. The solution is that all of these assume, in one manner or another, that infinite causal chains are possible. And so if we just rule that out, we have a simple, unifying, elegant solution to all of these paradoxes. And hence we should adopt causal finitism. And I guess by way of implications, I guess there's just one implication that I want to bring forth is potentially with regard to theism. So if causal finitism is true, then what we get is that there is an uncaused being, because first of all, there are obviously causal chains, and those causal chains cannot regress infinitely, and so they can't be circular, because that amounts to a certain kind of self-causation, and also circular causal chains are also a kind of infinite causal explanation, because C1 is explained or caused by C2, which is caused by C1, which is caused by C2. That violates causal finitism, as Proust points out in his book. And so we can't have a circular causal chain, and we can't have an infinite causal chain, and we do have causes, So we have at least one finite causal chain, in which case go to that first member. That first member is uncaused. So we have an uncaused being, and then we can leverage different reasons to think that, well, contingent things are caused by some sort of, whether deterministically or indeterministically, by some sort of prior condition. And so whatever is uncaused is such that it's a necessary being that caused the chain to begin and to get going. And so that in and of itself is an interesting result if it's true. And so that's at least one implication. And so I think that suffices for this presentation. I hope you thought this was enlightening. I certainly enjoyed it. I hope you had fun with the chickens, and maybe you were eating some chicken tenders while you were watching this. Hopefully you had ketchup, or rather than barbecue sauce, with your chicken tenders, though I guess I can't really judge you. Well, I'm Joe Schmidt, and this is The Majesty of Reason. Thanks for tuning in to Paradoxes of Infinity. Peace out.